by way of kind of beginning, I've noticed this folder came at about the time the midterm occurred. If anyone recognizes this, they can have it back. It's full of 101 material. It's clearly someone's study folder. All right. Then, second thing, it's going to rain by the end of today, but not during the day. It may spin a little bit, but by the end of the day, it's going to actually rain. I detect a low energy status from most of you. You're quiet, calm. If you can find time for a nap sometime today or tomorrow, man, that would be good for you, given the stresses of jump starting the quarter again. I mean, I had them too. I'm going to take a nap after my exercise. I believe on Friday, the evaluation system opened up. You guys know a lot more about this than I do. How long? Usually it's like a week. You have until the end of this week to finish evaluations for the course. Remember, unlike most faculty, I actually listen to you, and unlike most faculty, my teaching ability is connected to my job. So if you actually say I'm doing a good job, I actually get more money or have more job security. So unlike tenured faculty where it just doesn't matter, I have to work for my living. So there you go. Remember that. Let's see. Had a full set of office hours yesterday so people could see their, what do you call it, midterms. I will also have my normal full set of office hours on Thursday. Again, trying to catch up and give you guys opportunity to see me. So there'll be a full set of office hours on Thursday as well. Nothing today or tomorrow. Canvas, we've used for the class all 3.1 gig of the allowed Canvas stuff. And so I pulled a few things off. If you go and try to find the first 4 podcasts, they've disappeared. And I did that on purpose. I thought it was more important to have tomorrow's lecture than stuff that was old. I've put in a request that they'll up our allotment, but it takes a couple of days. You'll also notice that because of all the pictures of naked people in color, yesterday's lecture just took a huge amount of megabyteage. It was like 250. And so I pulled it off. And I will post up something that uses less space. I'll sort of condense out the slides of that lecture in a moment. I mean, the next day or two. So you have something to review, but it doesn't jam up the works. That all make sense? Okay. So I'll have a little beginner topic, and then we'll have today's lecture topic. Someone has pointed out to me that in your review notes for the pulmonary lecture, it says there's some sort of question about, so can muscles outwork lungs? And this is sort of you notice the 2 lectures I gave you on when I talked about pulmonary versus respiratory, most of the enhancement in oxygen transport and use is at the cellular or the cardiovascular levels. So the lungs themselves change very little, but that's okay because the lungs were already perfect. They were already the biggest link in the system. So when we talk about outworking one's lungs, watch the deductions you can do here. That if you have mitochondria, what I mean by outwork is if you're doing aerobic work and somehow you have a mitochondrial volume that can consume 3 liters of oxygen a minute, and your pulmonary diffusional maximum is 2.6 liters a minute, can everyone see what must be happening to the arterial oxygen content if each cycle you're removing more oxygen than can be replaced? Does everyone see it? That you would have progressive arterial deoxygenation if the lung couldn't replace what the muscles had removed. Now, I will only show you this one more time, this big set of figures, but it's easier to take it in pieces. End-tidal carbon dioxide and end-tidal oxygen measured in the deep throat do reflect what the final arterial values are. You don't have to put in an arterial. You can put it in an arterial line. You get the same data. So this is progressive work, and these 2 numbers are indices of what the arterial blood gases are. If we were outworking at high intensity, if our lung couldn't refill the arterial system with oxygen, what we would see is the arterial oxygen, indicated by this, would start to drop. Is that what you see? No. And if the lung was inadequate to clear all the carbon dioxide that was being poured out by the muscle, you would see the arterial CO2 begin to rise. Is that what you see? No. And so for most people, they cannot outwork their lung. Their lung remains the largest of the links in the oxygen transport CO2 shedding system. And so this is very typical that if anything, at maximum work, the lung is overventilated, driven by neural sensation, compared to what you actually would need. Does that make sense? Now there's two groups of people who can outwork their lung. That's probably worth mentioning then. People with broken lungs. So if you smoked for 40 years and have destroyed 30 to 40% of the tissue in your lung, well, yeah, that becomes the weak system. And one of the interesting things is, so this model, we use this in medicine all the time. One of the easiest ways to detect if someone has significant diffusional lung disease, you put one of those little oxygen monitor clippy things on their finger that measures arterial saturation, and you start them walking on a treadmill. If at any point they begin to desaturate, they've outworked their lung, and in an older person who has some sort of source of damage, that implies they've damaged their lung really badly. So arterial desaturation. The other group, there's only one group that they actually have more mitochondrial volume than they have lung, and that's something like 30 to 40% of Olympic level endurance athletes. So Olympic cross-country skiers, Olympic marathon runners. So think about it, they spent 15 years adding mitochondria and have finally reached the limits of their lung. The rest of us will never get there. All right, so for the most part, the lung is the most perfect and least changeable of the links in the oxygen transport system. If that helps you, someone, I can't remember, someone pointed out to me that there were review questions about that, and so now you know. So today is a fun lecture, and it gets back to this issue of where does this extra blood volume, you guys right now realize we retain extra blood volume, but how? How do we do that? So we'll talk about fluid balance during exercise. That's me, that's my training partner Ron. I'm drawing his blood while he works at 65% VO2 max with his arm in a sling. I'm measuring the blood flow in his forearm. I won't tell you what he has in his rectum, but anyway, it's a lot of fun. You're supposed to drink 8 glasses of water a day and exercise, but it's so hard to do. I know. Oh, do you keep spilling the water too? She thinks you have to drink it while you're exercising. Many of you, like many of these things that we hear, 8 glasses a day, I'll show you where that idea came from, but it's basically wrong. And the World Health Organization actually did a review, because the World Health Organization is very confused about concerned about worldwide human health. So clean water is a big issue, and how much. They decided you cannot say a fixed amount. It doesn't work. What you can say is for most humans, they will need about 1 ml of water for every kilocalorie of energy that they expend that day. Now I really love that one, because that means someone small like Dania, when she's at rest, if she has a day where she just binge watches Game of Thrones, she could easily get by on a pint of water and food. That's all she needs. If, on the other hand, Dania takes up a big training program and she's working out 4 hours a day, she could easily be 2 liters behind by the end of the day and need massive amounts of water. Does that make sense? So this is a very important figure to know. It's a sliding scale based on how much energy you expend. Does that make sense? Okay, so none of this 8. Funny, on the news, I listen sometimes to people say this. Remember, a glass is not a unit of measurement, right? So I've heard people say 8 cups. I've heard people say 8 pints. I've heard the other day it was really hot, and someone came on, the news person said, remember, you need 8 quarts of water. It's like 2 gallons. Yeah, it's ridiculous. Anyway, so let's talk about the water we have, and then we'll talk about how we can alter the amount. So here, out of the total body mass of, let's say, a 70-kilo person, let's go first where the water isn't. Because 85% of each fat cell, each adipose cell, is a big lipid dropule, water and fat don't mix, and so in adipose tissue, there's hardly any water. Each cell has a little demi-lune that's equivalent to about 15% of its total mass that has fluid in it, water and enzymes and mitochondria. But if you take a normal fat mass, someone around 20% fat, there's less than a liter of water in there. So what that means is, what I've just told you in a kind of cumbersome way, is most of the body's water is in the lean tissue. And the lean tissue is the most reliable because in a cell, the cell water is almost fixed. Cell water doesn't change greatly. It's a regulated value. So in the lean mass, if you take out the solids, so collagen and bone mineral and iron and hemoglobin and blah, that's about a quarter of the total lean body mass, which means that something like 75% of the lean body mass is water. So when you hear people say, oh, we're 70% water, they're talking about your lean tissue. Now, so here's all the water. And that comes out quite a bit, something like 40 liters of water of lean tissue in a 70-kilo person. So notice we have intracellular volume and extracellular volume. This is the side that's really quite fixed. The cells must pretty much maintain their osmolarity or they don't function right. And so this side is pretty fixed. I really like the way they've drawn this because they put the blood volume as having two different parts. It has a purely liquid extracellular part called the plasma. And then it has a cellular component called the red cells. And those are combined. Notice how they've also put the blood volume in the middle, almost as though it's circulated around between the extracellular fluid, which is the interstitial space, and the cellular space. And of course that's actually true, that the whole point of the blood volume, is to move around through this and equalize and redistribute fluid, heat, carbon dioxide, oxygen, glucose, fat. So that's its job, is to wander around these components and equalize their contents. Is that sensible? Okay. Just to remind you, look how much water is interstitial. This is our most flexible water, is the fluid between the cells, the cell bath. And so the plasma volume and the extracellular fluid are the parts that can kind of flux up and down. Okay? So you're going to see curves like this for the next 3 days. This is called a homeostatic curve. And the way you recognize a homeostatic curve is this flat part of the line, the y-axis is some sort of regulated variable. So I'll tell you right now that body water, I guess, concentration is regulated so that plasma should be around 300 milliosmoles per liter. It's very similar to cells. And notice that over a very wide range of environmental water amounts, your body will hold that constant. So you can have as little, we'll do the math in a moment, but as little as 1,200, 2,000 mils of fluid intake a day will hold you constant. That comes out to a pint of water plus some food. And if people are working very hard, occasionally you find people who during finals just start drinking water for no apparent reason to stay awake. Try not to do too much of that because ultimately you'll dilute yourself and become quite sick. But people who are laboring heavily or exercising in athletics can take in multiple liters of water in the valley. Is that okay? So that's just a homeostatic curve. It's also important to notice that if you push homeostasis hard enough, you can create dehydration or hyperhydration, and both of those are not good. All right, so let's think about, again, the whole class has basically been a study in balance and accelerated change, flux. So in a day, Here's would be where we got food or water from. This is saying roughly about 2.5 liters a day. I want to start with the waters of oxidation. This 350 mils, which is not nothing, of water, is a byproduct of our just resting metabolism. So you make water. Remember that. I mean, not make water in the toilet bowl. You make water inside your body with your mitochondria. And that's often called the waters of oxidation, right? Think about, by the way, if you're exercising hard, you actually up your water creation. Kind of interesting. Then you guys think of your water as coming primarily from these two components, and you probably are overestimating fluids. And in fact, I would flip these. Normally, about 60% of your water intake comes from food. 60% comes not from drinking things, but from the food you eat. Even a well-cooked steak is more than 50% water. If you ever, you can't afford it, but I can. You barbecue a steak, you make it pretty well, then you put it in a vise between two boards and squeeze it. A tremendous amount of water comes out of it. Apples are 90% water. So tremendous amount of water. Unless what you're eating is crackers and jerky, a huge amount of your water input, the majority, is coming from your food. And then that amount is at about that's 1 liter is actually being consumed by drinkage. By the way, those aren't the minimum amounts. I'll do the minimum amounts in a moment. And then here's what's coming out. Among the outputs, the ones that are the most intractable are you can't stop respiratory water loss without stopping breathing. I guess it slows way down in a humid environment, but in most of the environments we're in, we're stuck with respiratory water loss. The skin is not plastic. It's a bunch of stacked up dead dead skin cells, and so there's a certain amount of leakage across the skin that is not sweat. It's called insensible perspiration. Just water loss through the skin. Your skin is not perfect. And then, let's see, feces, that's, they have to be soft enough to get them out. And so the urine is really the adjustable one. If you over-ingest fluids, I think some of you did an NPB 101 lab, right? If you over-ingest fluids, you then produce a lot of urine within the next hour. If you under-ingest fluids, it reverses. So the flexible one is that. These others, well, you'll see. Now, the next concept I want to introduce is the idea that we must lose water. Obligate water losses. Humans have no way to shut off. Like I said, the skin's going to leak because it's going to leak. And if you want to breathe, you're going to lose water vapor. So I really like this figure. See the guy's exhaling and cool, like today. And there you go. And it reminds me of that old Police song, every breath you take, every move you make, water is leaving you, are the lyrics. I could be wrong. So everything we do tends to lead to obligate water losses. And so I want to return to this figure and draw right over here. I want you to say minimums, because there's certain minimums that you cannot go below. So the easy ones are, water is going to, these are not going to change. These are as low as they can go. So those are obligates. Feces, that will become very hard if you try to remove water, so those don't change. The one that can change is urine, and this urine output is in a fairly wet intake environment. If you start to restrict water, this can be cut down to about 400, 500 milliliters per day. Is that okay? Now, does everyone see why you can't have urine go to 0? Does anyone that, I'm doing the math up there, your glomerular filtration rate, if arterial blood reaches the glomerular tuft, you leak. And that leakage amounts to, you filter your entire plasma volume about 3 times every hour, right? So your plasma fraction actually leaves your body 3 times an hour and then is actively resorbed. Well, let's presume that that resorption in a state of fluid conservation is really good. Let's say you're resorbing 99.5% of the fluid that went into the tube, the renal tubule. Does that sound pretty good? Well, that adds up to 500 mils in a day. So even with 99.5% perfect reabsorption, you're going to get a cumulative loss in the kidney. So is that okay to write those obligate losses? Oh, by the way, that comes out to, once you do that and add these up, you'll discover that humans in extreme water conservation can get by on a pint of fluid a day plus food. The British Navy has known that for 500 years. If you're running low on water, a pint for each soldier, each naval person a day, and food. That'll get you there. They'll have some pretty stinky urine, but they'll live. So, during exercise, in a normal day, exercise is by far the biggest threat to our fluid balance. What is it about exercise that creates a tremendous, and particularly for the cardiovascular system, there's a danger of collapse. So what are the two problems during exercise that are robbing us of our fluids, especially our plasma volume? One of them you know right away, so go ahead and say it. Sweating, yay! Then the one that we skipped a little bit on our cardiovascular lecture, because I ran out of time, is that the onset of exercise, when you first start exercise, you cannot open 1 billion new capillary beds in the muscle that's working and put those capillary beds under higher pressure and not have them leak. It is the nature of open capillaries to leak. And so you may not have known this, but when you start to exercise, within about 10 minutes, there's a plasma volume loss. You squirt your blood out into the working muscle, and that squirtage is proportional to how much muscle you open and how high is the pressure. So in the workouts that you guys like, 5-liter blood volume, 10%, so half a liter, a pint of fluid is gone within the first 10 minutes of exercise. By the way, for those of you who are aware, right before an event, I've told you over and over, don't put food in your mouth before a performance event. However, in the 15 minutes prior to a cardiovascular performance event, putting roughly 1 pint of fluid into your body is a hugely good idea, because this means when that shifts out of your circulation, this can shift out of your gastrointestinal tract to resuscitate the plasma volume loss. Does that make sense? So prehydration before a competitive event is a very good idea. Does that make sense? Yes, ma'am. Oh, sure. The number of capillaries that you open up, Mariken, so here's 40% VO2 max. Here's a higher workload, and so that would be more capillaries are open due to the higher workload once you get the adjustment. And then the pressure that those are seeing, and remember we slightly raised the mean arterial pressure in proportion to the workload. Yeah, Drew?
So are you saying it squirts out? Where does it squirt?
Oh, it squirts into the working muscle. So transiently, your muscles are turgid with fluid. Let's switch from cardio to weight training. As everyone has noticed the pump, when you lift weights repeatedly and then you look at yourself in the mirror, the particular muscles you've used appear bigger. They are. Now, that's not protein. You haven't synthesized protein that quickly. It's fluid. You've engorged your muscles with plasma volume fluid.
So you have less running for.
Got it. And as you've noticed, to your great disappointment, the pump goes away about an hour after the lifting, that you cease to look as cool as you did right at the end of the workout. Of course, it revascularizes, Drew. And so at the end of exercise, everyone always wants to call this sweat loss. It's not sweat loss. When you stop the exercise, and I wish I had that data, it pops right back up. If you take a blood draw at the end of the work, wait 10 minutes, it reappears, draining out of the working muscle back in the circulation. Is that okay? Okay. So then the one you knew is this one. I think this is me. So working at 60% VO2 max, which is a very pleasant workload, it is easy to lose over, that's a liter and a quarter per hour. Very easy to lose that or more in a well-trained person. Sweat loss is the big one, but it happens late, right? It takes an hour for this to accumulate. The plasma volume loss is right at the beginning of work. And plasma volume loss is what we call intracorporeal. It's inside the body. The fluid's still there. It'll come back. It's just not available. Okay, are you ready to talk about what we do about this? What we do about this, so here's someone who's having those effects. That's my buddy Ron. He's being asked to exercise for 70 minutes for my master's thesis. This is showing you what happens to the balance. This is the figure, I think, in your posting it says this figure is under construction or something. It's from a book, and they made one of these typical mistakes where they said they wanted to make it hot weather or exercise, and you can't do that. They're different conditions. So they tried to combine too many things. When you look through where the losses are coming from, if you were just sitting quietly in a desert, would your breathing double? No. And this, if you go back and compare it to rest, the breathing has doubled. So I went and back calculated what this situation is. This situation is either 8 hours of labor, like a roofer or a street worker spreading macadam, or it's 3 to 4 hours of hard exercise like a marathon run. And it's in moderate temperature. And so what you see is there's increased water loss from the lung if you're exercising. The main increased water loss is the skin. Notice how the urine in water fret will automatically, your kidneys, I told you, they were the most flexible control of output. And so if you're hemorrhaging water, I shouldn't use that word, if you're leaking water from a lot of other places, you will cut down your renal losses, and that's the mechanism we're going to talk about. Everyone see the difference? Okay. So, and one of you deduced what Dr. Adams used to talk of as the paradox of water during exercise. You would like to spread water all over your skin for the purposes of heat loss, but you would also like to keep the water in your central circulation for the purposes of doing the work and transporting the heat to the skin. You see that problem? And so one solution that I will hint for tomorrow's lecture, one solution is just simply have more total water. If you have just a bigger blood volume altogether, you can share more. You can accomplish both. So this slide is your summary, your quantitative summary slide of the next 3 color pictures. And what we're going to do, let me describe the experimental method. You take the grad student and you hydrate it. And there's a way to do that. You take 10 mils of fluid for every kilogram of the grad student's body weight. They have to drink it the night before. They then come into your lab, and they ought to pee pretty copiously by the morning. You give them another bolus of that. You measure their urine to make sure they're perfectly hydrated. You measure urine-specific gravity. And then you give them another bolus of 10 mils per kilogram of body weight just before you start the intervention. So they're perfectly hydrated, and you just shoved a bunch of fluid in them. So as you know from your MPB 101 lab, what will happen is you'll get roughly the same amount of fluid you gave them will come back out as urine in about an hour. So here's that condition where the grad student has just showed up, you give them a bolus, and you wait for like an hour, and it turns out they will give you 98% of that fluid back within the hour, a urine flow around 6 mils of urine every minute is being filtered, and a concentration that approaches what's called isostin urine. It's the same as the plasma. The kidneys are neither working to shed nor retain, they're just passing it on. Make sense? Okay, now, what you're going to see is the effect of either the intensity of work or the duration of work. And the take-home point is, the more exercise you do, whether in terms of intensity or duration, the more your kidney shifts into a water retention state. So here's the grad student on the day they did no work, and there's all the fluid I gave them, except it turned yellow. That's what they did. Then have them do an hour of 25% VO2 max. This is walking at like 80, a heart rate of 80. It's very gentle. It's what old people do. But still, notice the urine is less copious. Sorry, I had to change, but this is like 750 mils, and this drops down below 500. So even a light workload concentrates the urine. And then look what happens. 50% VO2 max is nothing. That's a hike of a heart rate of about 120. And look what's happened. It's very sad. Oh. Seen it? So intensity seems to restrict urine flow. And then this is the effective duration, because I had the grad student come in on 2 different days and do the 50% workload for half an hour and for a full hour. And so you see that there's a progressive effect. If anything, it looks like intensity is the most important, and then duration is a secondary concentrating factor. Is that all making sense? And so here's all the colors of the rainbow, all the shades of. So, exercise induces a state of fluid conservation proportional to intensity and duration. So we're going to spend the rest of the time talking about how. I have to show you one. I always like it when other people reason to the same point. So that, I don't know if you guys know about the Western States 100, which is a 100-mile foot race on the trails of the Sierra. It starts around, it goes to Auburn from, where do they start? They start near Tahoe. Squaw Valley, yeah. So this poster is at 55 miles at the Robinson Flat Medical Point. And look how they figured out the same thing, that if your urine looks like that, you're drinking plenty and in fact don't need to drink more. If you're in this range, this is okay to become. If your urine is this color, black usually associated with blood loss. So something bad is happening, you need to go to the medical tent. But I like the idea that the best way to indicate hydration state is to check with the kidneys. So, now the rest of the lecture is mostly about, so how do we do that? How do we alter the kidneys' function? The first one is easy, and there's an emergency room dictum that if a patient comes in and their blood pressure has collapsed, right, there's very little blood flow, they stop making urine. And so the thing we say in the ER is no BP, no PP, right? If urine can't make it into the kidney, blood, how can it get across the glomerulus? Does that make sense? Okay, well, it turns out that in exercise, remember, we actually do turn off kidney perfusion. So a significant fraction of this water retention is built into the very first minutes of exercise response. You shut down the guts, including the kidneys. And what does not reach the glomerulus cannot be turned into urine. Does that make sense? Okay? And remember how I said you're not learning a lot of new stuff? We already talked about this. Here's a work rate. You guys would normally choose to work around here. If you do that, your renal blood flow is about half of what it would normally be. So at least at the kidney, the rest of your blood pressure is fine, but at the kidney, no renal BP, no perfusion to the kidney, no PP. Now, what little fluid, the half of the fluid that is reaching the kidney and being filtered into the renal tubule, comes under a heavy hormonal endocrine influence for reabsorption. So watch. Let me bring in a line. These are stresses. These are things the body doesn't want that are imposed by workload. The plasma volume is dropping in proportion to the workload because you must open up capillary beds and pressurize them. They therefore leak. Notice that the plasma is becoming more concentrated. Plasma sodium is rising. So, down here, the reason I put in a red line is to distinguish. These are stresses. These are not things the body wants. Remember, I've taught you that if anything is a hormone or a nerve action, that's not a stress, that's a response. That's the body trying to limit the damage. And so notice what we have as response. Arginine vasopressin is also known as the anti-diuretic hormone, which causes resorption of water from the distal renal tubule. True that? And then this thing down here, PRA, stands for plasma renin activity. And I'll review for you what renin. Does everyone remember renin? We'll do it in a second. So the combination of these two lead to water resorption. I'll go through renin briefly. So first off, you'll hear many people ostentatiously say renin. And to be quite honest, it's far better to call it renin. It is the renal hormone. It's the hormone from the kidney. When you say renin, you open up the ability to have terribly confused discussions with people like Dr. Batista who like the gut. Renin is a coagulytic protein that curdles milk in the gut of ruminants. And so you have these very confusing conversations if you call it renin. I guarantee you, you'll talk to someone like, what are you telling me? Renin is the renal hormone. So, renin is secreted by the juxtaglomerular apparatus. Remember, that sits right on the afferent arteriole. So this is monitoring the BP. This makes the PP. And this creates the hormones to deal with that. So renin is an enzyme, and what it catalyzes is the conversion of pre-angiotensin, which is called angiotensinogen, the generator of angiotensin. And it converts this to angiotensin 1. Angiotensin 1 is not terribly active. Then, as soon as renin has catalyzed angiotensin 1, it circulates through the body. The lung vasculature has a huge amount of the angiotensin converting enzyme that converts angiotensin 1 to the highly active angiotensin 2. I'm covering the answers. So what does angiotensin 2 do? Let the word help you. It tenses your angios. And so angio is a Latin word for blood vessel, and it tenses them. So angiotensin is a vasoconstrictor. It's helping you maintain blood pressure as the exercise goes on and you start to reopen your blood, your skin, and you start to run out of fluid. It's tensing up the vessels in any non-active part of the body to maintain blood pressure. Does that make sense? Does anyone remember the other thing that angiotensin does? It stimulates aldosterone secretion from the cortex of the kidney. So aldosterone is stimulated. Now, aldosterone causes sodium retention, which is another way to limit fluid loss. Got it? So trying to stabilize blood pressure two ways is angiotensin 2 by constricting what vessels you have and by making sure you limit the amount of further water loss. This arginine vasopressin is causing water resorption as well. So those two mechanisms plus the lack of blood flow into the renal artery are the reasons we darken our urine. Does that all make sense? Okay, that's some hard physiology. I want to point out that at this point you've now had your endocrine lecture. It just wasn't given in one day. It was scattered over several. This would be a fun thing to do with your notes, is try to look at the three different places where we talked about hormones. Hormones during acute exercise, during one bout, do three things. They help you redistribute blood flow. They help you get the fuel you need to the cells that are working. And now we're saying they help keep your liquid and electrolytes in balance. So, right? So that's all they did. And I just scattered that over three different lectures. Now, the last part of this lecture is to think about what these hormones, so the hormones get us through one work bout. That's their immediate job, is to survive this exercise bout. But very often, the hormones have a longer term effect, especially in the recovery period, that changes us. Does that make sense? For instance, what if you finish exercise and your aldosterone is really high, right? I'll show you how high in a moment. And you happened in the 2 hours after exercise to eat something with sodium in it. What's going to happen to that? Normally, remember, in a balanced state, putting things in your mouth doesn't create fitness. You just pee them away. So salt in, salt out. But if you do it with high aldosterone, where is that salt going to? It's going to tend to stay and add to your total fluid supply. So watch this. And the reason I'm emphasizing this is that each workout will create changes in endocrines and genes will get activated. Very often in the recovery period, just like mTOR gets activated during the work, but it does most of its tricky stuff in the recovery period, synthesizing more protein in case you do the workload again. All right? So watch what happens. you finish, this is Vic Convertino's study where he did 2 hours of work at a reasonably low intensity. Notice they've lost 10% of their plasma volume, their osmolarity has climbed in their plasma. They've increased their arginine vasopressin by 840%. These are not small changes, these are big old changes. And their plasma renin activity has gone up by 1,000%. So these are big honking changes. Now, think about the water that you guys are drinking now is next hour's urine. What's going to happen to the water that these people, by the way, where do you suppose these guys went when they dismounted from the bike after 2 hours of continuous exercise? Where's like one of the first stops? Anyone know a side effect of arginine vasopressin on the central nervous system? Increased thirst. If you inject arginine vasopressin into a rat, within 5 minutes it'll be in its water bottle. So, kind of cool, but not only does it cause water retention, it stimulates our centers of motivation to cause us to be thirsty and seek out water. So, what will happen to the people who, as they dismount the bike and go drink a pint of water, if normally they would excrete a pint of water an hour later, what's going to happen to that pint of water if they drink it with this endocrine state? It's staying. Am I making sense? Not all of it, but a much bigger fraction of it is going to stay. You've done this where you have a really hard workout and you drink a whole bunch of water, nothing happens. I was like, oh crap, I've destroyed it. And then you drink a whole bunch more water. It's like, and finally, like 3 hours later, you bust loose with some urine. Am I making sense? That's what's doing that. Okay, very cool. Remember then, because Vic did his study over 8 days, they did this same workout every day. And remember, so if in that recovery period, it's so much like the hypertrophy in weightlifting. If you keep turning on this recovery period change in protein expression, it's going to start to add up to something. Here's that plasma volume increase of a pint in 8 days. So the hormone change that's getting you through the one workout is also lingering in the recovery period and causing your intakes to actually be distributed to useful places in case you work out again. Does that make sense so far? Okay. I only have one more figure, but I'm not sure how well it's been taught to you. Dion, I think did any of you have Dr. Usre for 110C? Okay, so I think he talked about this, although you may not have gotten it. Remember that in a capillary, where the pressure in the capillary is something like 30 millimeters of mercury, the tendency is for the fluid to squirt out at the front. The thing that keeps fluid from leaving the circulatory system, we use an osmotic effect exerted by globular proteins. Albumin is by far the biggest one, and the osmosis created by protein has a special name. We call it oncotic. Oncotic is the water draw, the osmotic draw, the suck, created by globular proteins. Is this okay? So what I'm telling you is, if all you did is retain fluid and salt, you just get puffy. It wouldn't stay in your vascular system. You'd wind up with puffy ankles and thick wrists. Not making sense? So what must you need? There's one more step. Endocrines alone is not enough. You need to actually change gene activation. So what protein would you activate if you wanted this fluid to stay in the cardiovascular system? Albumin. One of the reasons I like this example so much is almost every one of these steps in the links were developed by UC Davis researchers. Vic Convertino did this endocrine part, and then my friend, my TA for EXP 101, what the equivalent was back in the day, was Gary Mack. And when Gary Mack, as a postdoctoral student, went to work with Ethan Nadel at Yale, Gary said, you know, because he knew that, we all knew this, that endocrines alone weren't enough to keep it in the cardiovascular system. It was enough to keep it in the body. And so by the time we got to 2000, we had the genetic techniques. We could actually look at the albumin synthetic rate. And so Gary Mack measured the absolute and the fractional synthetic rates. And so the long story short, in the post-exercise period, your albumin synthesis bumps by something between 10 and 15% and stays up for several hours. Very much like the mTOR-driven synthesis of sarcomere protein. And as a result of, if you've retained 20% additional fluid and you've increased your albumin 20%, well, most of that fluid is going to stay in the vascular system. Does that make sense? Isn't that cool? Just since we have a tiny bit of time to tell you about an interesting clinical issue, I have long thought, because most regular exercisers are walking around with somewhere between a pint and a quart of extra blood, realize that they're going to survive hemorrhage better. So whether you're a mom who's getting ready to deliver her baby, who's going to be bleeding, I'm so sorry, or someone on the street who's come off their bicycle and had a bad limb break, you're going to tolerate that better, not only because you have a better heart, but because you can afford to leave a pint of juice on the pavement. Athletes are juicier people. Make sense? Okay. One of the interesting problems when you're dealing with other people who aren't athletes, when you do a surgery or you have a gangbanger with a gunshot wound, is you often need to resuscitate them with fluid, IV fluid. And the problem is, if you just pour salt water into them, where does it go? Everywhere. Right? It goes everywhere. And so this ability to stimulate albumin synthesis, if we can figure out, I think it's the liver that's doing this, if we can figure out the signal for albumin synthesis, you can help a lot of people who are hypovolemic, who are losing blood for a variety of reasons. By the way, what we do these days, we infuse in the IV fluid, you can put in what's called colloid, you can put in manufactured proteins to imitate what albumin does. It'd be better if the body would make it. Does that all make sense? Very good. So exercise literally makes us juicier. It specifically expands the plasma volume, which is the critical circulating water volume, but it makes us more waterier, that's a word, overall. And tomorrow when we start, I'll have a little afterthought about just how juicy are we after training. It's kind of cool how it adds up. See if you can't get some sleep today sometime. I plan to. I can tell you're tired. Let's see, Jai, you told me to fix this. Oh look, I fixed it on this one. I guess I must have posted an old one. Because this one is right.